symposium on a topic multi-phase flow, because this is one topic where lot has been done by both mathematicians as well as the engineers. But
good morning. Can you? Hello.
Good morning.
Hello.
Yes.
Yeah.
Yes, good morning.
Yeah. So Señor Ramos is here. Hola, Señor Ramos.
Hola.
Yeah. Buenos días, Señor. Thank you
Buenos
very
días.
much. Sorry to disturb you at these early hours in Spain, España. Okay. So thank you very much. So yeah. So we really appreciate your efforts. When I asked the first time without any hesitation, so he agreed to organize the mini symposia. So we are very much thankful to all the speakers. So within the short span of time, we will be able to bring all the people over here. So I'm really very much thankful from our side of ADENA, okay, to the speakers as well as the organizers. So now I request Eugenio to come. Yeah, please, carry over. So again, muchas gracias, señor. So thank you very much.
Okay, thank you very much to you.
Yeah, please go ahead. We are waiting to hear from the speakers.
Okay. So our first speaker is Professor Abdul Mahid. So she's talking about multi-step block method for solving neutral delay differential equations. So when you are ready, you can go ahead, please.
Okay, I try to put my slide. Can you see my slide?
Yes.
Yes.
Oh.
Not now.
Okay. Okay, can you see my slide now? Okay.
Yes.
Okay. So okay, so this is okay, so hopefully everybody can see my slide. Okay, firstly, I would like to thank you, Prof. Gino Ramos, for this invitation, for me to join this conference and for this mini symposium. Thank you very much.
Excuse me, if you don't mind, can use the control L so that we can see the full screen, please.
The full screen, okay.
Yeah, control L will give you the full screen. Sorry for the disturbance.
Okay, can you, is it okay?
Yes, it is perfect now. Yeah, please go ahead.
Okay. So the title of my talk today is multi-step block method for solving neutral delay differential equations. So this is a research of together with my postgraduate students, Nur Inshira. Okay, but this is for her master thesis, but now she's proceed for her PhD. So next is the delay differential equations, just to as a very brief introduction of a delay differential equation. So as you know here, where the derivative of some unknown functions at present time are dependent on the values of the function at previous time. Okay, so therefore we might say that we are calculate at the present time the value that we would like to find, but yet there's a previous time for the function that we also need to calculate. And then, of course, there's a time delay system, equations with deviating arguments, and also ODE with time lags and retarded ODE. Okay, next, just to highlight to you the difference between the retarded DDE and neutral DDE. So we look at the first equations. Okay, the first formula, you can see that we have there's a tau there. Tau, that is the delay. Okay, the delay in this first order delay differential equations. And you can see that we have the y prime here, but on the right hand side there's no y prime. Compared to the equation number 2, you can see that we have y prime, and on the right hand side there's another y prime. So that's the difference between the retarded DDE and also neutral DDE. So that's why equation 2, as you can see, that it is a neutral DDE because of there's a y prime on the right hand side. And then we go to the type of delay that usually that we go for our research. Okay, there is a few types of delay. We have constant delay, time-dependent delay, state-dependent delay, even pantograph equations, and so periodic delay case. But for today, just to share with you what we have discovered for the block method is to solve the first case, that is constant delay, and also the fourth case to solve the pantograph delay, where the Q is between 0 and 1. Okay, so the objective of my presentation today is to show to you the derivation of the implicit multi-step block method with off point using the Taylor series polynomial. And then I also going to discuss the order, convergence, and safety region of the method that we just developed. And also we're going to share with you the implementation that we have done to solve the method that we developed to solve NDDE for constant and pantograph delay, where we have solved using the C language or C programming by constant step size. Okay, so just a few literature review related to the neutral delay differential equations. Well, Ishaq in 2013 have developed a 2.1 block method to solve the pantograph delay. And for this, Ishaq, she has used the variable step size to solve the NDDE. And then Ishaq and Ramli in 2015, they has proposed a 3-point implicit block method to solve again the first order NDDE, also using variable step size. And then Xiong and Majid in 2015 has proposed a fully implicit block method as in the form of predictor character Adams-Morton to solve the first order NDDE of pantograph type. So the method that we're going to develop actually is we call it as a hybrid multi-step block method with one off step. Then continue to the hybrid block as far as our concern as we look in the literature. From this author, you can see that they have developed Yakusa and Adeniyi developed the hybrid block method, and then Abderrahim also again developed a hybrid block method, and also again in 2018 by Ajileye again to develop the hybrid block method, but yet to solve first order ODE, and maybe they have go to higher order ODE, but as far as we concerned, there's none that have tried to solve the hybrid block method to solve the neutral delay differential equations. So this is a very brief. We describe the derivation of the 2P1H4. We call the method as a hybrid block order 4. This is the predictor formula. So as you can see here, this is equation 3 is the linear multi-step method with off point. We can refer this in the book by Lambert. And then what we're going to do is that we are going to expand in terms of Taylor terms or Taylor series for the y-axis and the f. Okay, f is also in equation 3. So we expand in Taylor terms and we will get as equation 4 here. Okay, so we have 1, 2, 3, 4 formula. Then what we're going to do is that we're going to substitute into equation 3. Okay, substitute into equation 3, and then we are going to collecting the terms, and we compare to 3, and we will get this. Okay, there are 3 equations that we can obtain, and we will solve, and we will obtain the value for the beta naught, beta 1, and beta 2. Okay, so these are the value for the betas. So then, okay, so we continue here, as you can see. So we substitute the value of the beta that we obtain, and this is the formula of the first point for the predictor of 2p1h4, okay, as equation 6. So we have on the right hand side fn, fn minus 1, and fn minus 2. And then for the second point, okay, because this is a block method of 2 points. So for the second point, again, we will proceed the same procedure as we mentioned just now. Okay, and we will obtain the predictor for the second point. So this is the predictor for the first point. So this is the predictor for the second point. And also we will find the formula for the off step point, that is at n plus 1/2. Okay, so this is as equation 7. Okay, then we go for the character formula, the same procedure as what we mentioned for the predictor. So the character formula here, as you can see, that we will have 5 formulas that we will expand using the Taylor formula. Okay, so this is what we have, and then we will compare with the same equation, the general of the hybrid formula, and we will collect the terms, okay, from equation 8, and this is what we will have, and we will solve to get the value for the beta naught, beta 1, beta 3, and beta v. Okay, so this is the value that we will get. Okay, so just a very brief how we derive the proposed method. So now this is the after we substitute all the beta. Okay, so this is the first point of the character formula of our block method. Okay, so for this is yn plus 1. So inside here you can see that this is the off step point at the point n plus 1/2. And then we proceed for the second point, okay, using the same procedure as the previous that I have mentioned to you. So we will get, hello? Okay, so we will get the second point as equation 11. So you can see that this is the formula for our character formula for the first point, and there's an off step there inside at n plus 1/2, and our second formula yn plus 2, there's an off step inside the formula at n plus 1/2. So this is the formula that we have obtained. Okay, so this is the block method. So this is the off point. So this is the predictor. Our predictor also in the form of a block method. And this is the character, and it is also in a block method. Okay, now we check for the order of the method that we propose. So we're going to refer to definition by Lambert. Okay, so this is the definition 1 as equation 13. So we will say that the method is of order P if we have Cp plus 1 not equal to 0. So that's what we're going to calculate. So we calculate and we obtain C naught is 0 until we find that at C5 it is not 0. So therefore we can say that the method is order 4. C5 equals Cp plus 1, so P is 4. And then we also check for consistency of the method. Again, we refer to definition in Lambert, and also we check for zero stable for the method that we propose, and we obtain that the method is consistent and also it is zero stable. Then again, followed by the theorem by Lambert in 1973, where the linear multi-step method is converged if and only if the methods are consistent and zero stable. So therefore, the method that we have shown, it is consistent and zero stable. Therefore, the method that we obtain is convergent. Then we're going to go for the stability. We also plot for the stability of the method that we propose. So this is the test equation related with the problem that we're going to solve, that is a neutral delay. So this is equation as 14. So this is also in the literature. Then we're going to apply the character of the method that we has proposed from the above formula into the linear test equation in 14. Okay, so then this is what we're going to do. We're going to replace the H1 equal HA and H2 equal HB in equation 15, and we will get as equation 16. Then we rearrange. Okay, we rearrange the term, the equation above, and we will obtain as equation 17. And then, of course, to find the stability polynomial, we need to find the determinant. Okay, so we will find the determinant as shown below, as is equation 18. So here we just need to check did we obtain the NP stability, because for when we want to solve the neutral delay differential equations, we need to find the NP stability. So the NP stability, the region of RMP is in the H1, H2 plane. If for any H1, H2 is in the region of NP. Okay, so this is the figure that we obtain. Okay, we obtain when we plot in Mathematica. Okay, so this is the stability of the method we propose. Okay, so now the implementation of the constant delay for the NDDE. So first what we need to do is that, of course, we need to find the location of the delay that must be determined in order to obtain the solution of the delay, okay, for the tau, and also the delay at the y prime, the delay at y and the delay at y prime. You need to determine the location. And then what we need to do is that we need to check in our program if the delay is less equal to A, then we need to use the given initial function. Okay, so the given initial function is here. Okay, this is in the question. So we need to use it to solve the delay terms. And for starting, okay, we will use RK4 to start, because as we know, multi-step method, it needs another method in order to start. So it will need RK4. So then the derivative of the delay terms will be obtained where we will use the forward difference formula. Okay, so we will use the forward difference formula as equation 20. And then when we obtain the delay terms, of course, we can proceed using the block method that we have developed to solve the NDDE. So this is for the constant delay. So now we go for the pantograph delay. Okay, so pantograph delay is slightly different from the constant because there's a Q there, you can see here, where the Q is between 0 and 1. Okay, and then if the Qx is less equal to A, then we will use the given initial functions from the tested problem. The problem that we're going to solve, we will use the given initial function to solve the delay. But okay, this is when the Qx is less equal to A. But if the Qx is greater than A, okay, so what we're going to do is that we need to use the Lagrange interpolating polynomial, where for the delay, as we know that we need to store all the calculation values that we obtain along the interval, because we need then to update and use the Lagrange interpolation polynomial to calculate the delay terms. Okay, for the starting values for the pantograph delay is different from the constant delay, as I mentioned just now. For the constant delay, we start using the RK4, but for the pantograph delay, we will use a modified Euler method, because pantograph delay is very sensitive. We have to, because at the beginning of the interval, we need to use a low order method, okay, in order to get a better result. So the derivative, the y prime, we will obtain using the forward difference formula. And then, of course, we will proceed and solve using the method we developed until the end of the interval. Okay, now is the numerical results. So in our table, we have the step size, then the total function cost, the total steps, also the time, average error and maximum error. And we're going to compare, so with the other two methods. Okay, this is the method that we developed. It's a 2-point implicit hybrid multi-step block method of order 4. We're going to compare the method in Seong and Majid. So this is a fully implicit method. Okay, so this is a fully implicit method. And then this is Adam Bashford Moulton method of order 4. Okay, so we're going to compare with these two methods. Okay, so first is the constant delay. So this is a linear, neutral DDE. Okay, so from this first example, okay, so we run for 3 different value of age. So we look at the first age at 0.1. Okay, for this constant delay, we can see that in terms of total step, both of this method has the same total step because both are block methods. But ABM4 is the common Adam Bashford Moulton method that we usually learn in the postgraduate class. So this is, you can see that is more than this block method. Okay, but the function evaluation is the same. But you can see that the method that we propose able to get a better maximum error and also less timing compared to the other two methods. Okay, this is at age 0.1. Now we look at the other two age. Okay, so you can see that in terms of accuracy, the method that we propose, the hybrid, able to obtain better accuracy compared to the other two methods. And also we have total step is half, okay, for these two block method compared to the ABM4. Now we go for the second example, is a pantograph delay. So this is linear neutral delay. So the exact is exponential minus x. Okay, now we look at this. Okay, for this pantograph delay, for these questions, we're able to get comparable result with the other two methods. And also, as usual, you can see that there's a slightly better in terms of function evaluation for the method we propose. We're able to get less function evaluation compared to the 2P1B4, where this is fully implicit method. And also ABM4, of course, it has more function evaluation here. So that's another advantage of the hybrid block method. Okay, now you can see the same as in example 2 as we go for the other two step size. Okay, where the result is comparable with the other two methods. Okay, now example 3 is the pantograph delay. So this is also a linear pantograph delay. Okay, so you can see that the method also that we develop here able to get comparable result with the other methods. Okay, but now you can see that for this 2P1B4, this is fully implicit block method. Well, it's slightly lower than the method that we obtain. Okay, but the method that we have is better compared to the fully implicit block method. Then we go for this is a non-linear neutral delay differential equations for pantograph delay. Okay, so the result we obtain as 3 different value of age, as you can see, that is comparable with the ABM4. Okay, but as the age getting smaller, you can see that the result we obtain is much better compared to the fully implicit block method. And also, as you can see that this is for the special for the pantograph. You can see that when the age decrease, the method that we develop has less function evaluation compared to this block method and also Adam Bashwan-Morton method. So therefore, that's why in terms of timing, the method we developed is able to give a faster result compared to the other methods. So conclusion, so we can see that 2P1H4 has shown its efficiency in solving the neutral delay, and the block method that we propose has produced less computational works as we have the timing. Okay, the timing, it shows that it's faster compared to the other methods, and also in terms of the maximum and average error, as the step size decrease, we're able to get a smaller accuracy, and also the method that we propose is suitable to be applied in NDDE problem with constant and pantograph delay type. Okay, so this is all the references that I have in my slide. Thank you for your attention.
Okay, thank you very much for your talk. Now, maybe somebody want to ask some questions. So it is your turn. Please ask any questions you have.
Is there any question? Actually, this is the same student in Shira, where this is the result from her master thesis, but now she's proceed for her PhD, and now she is solving the neutral delay for Volterra integral differential equations, and she able to get a very good result, still in block method. So I'm quite happy with the result that she's obtained now. And also for the delay differential equations, I also go for the higher order, but of course for today's presentation, I did not share the higher order delay differential equation with all of you. And maybe next time. Today just for the first order neutral delay differential equation.
Okay, maybe this for the next time, next conference.
Yes, I'm not sure when. Maybe next conference.
Okay, I want to ask you something about your presentation. You have used a predictor-corrector mode. I want to ask you how you try the same block method, the corrector method, as a fully implicit method to solve the problems, and to compare with the predictor corrector mode?
No, how I compare it, the predictor and the corrector. I'm not sure if I answer it wrong. Maybe you can ask me again. The predictor and corrector is in the block method. So that means when I solve, that means the process is that it will go for the predictor and they go for the corrector. But I did not iterate. That means I only do it for PECE only. Predict, evaluate, correct, and evaluate. But somehow in the method that we have here, as you can see, okay, I show the, okay. So now, as you can see, this is the block method that we have that compute and give us the solution. Okay, so what's the advantage compared to the fully implicit method by Hu and Majid? As you can see that I compare in my result, because in Hu and Majid, in that case they are proposed the fully implicit. But now, if you look carefully, in my Yn plus 1, I didn't have Fn plus 2 on the right hand side. Okay, but in Hu and Majid, they have Fn plus 2 on the right hand side. So that's why they have extra calculation of the F. But in our case, we did not have the Fn plus 2 at our first point. So that's why we able to get better and faster in terms of timing compared to the fully. So this is, we can say that is more of the diagonally implicit hybrid block method. Did I answer your question, Prof. Ramos?
More or less. The question was about your method. If you have used your method, but not in predictor-corrector mode, just a simplistic method, because the method you propose, the corrector one, the block corrector, I think is presents some advantage over the other method you mentioned, because the first equation, as you said, there is no n+2 in this, so you only have to solve this equation, this simple equation, and similar for the second formula, where there is only n+2. So my question is, if you had tried your method, but not in predictor-corrector mode.
Oh, okay. If I didn't have the predictor, that means, of course, the multi-step method need to have a predictor. Okay, we can't it can't stand alone only by the character. We need to have the predictor. So unless I develop an explicit block method. So if explicit block method, I won't need to have a predictor. Okay, but in this case, because of I'm using the predictor character, so that's why I need to have the predictor. For example, the Runge-Kutta and Euler method only at the very beginning, as the initial only that I will use, only at the very beginning. Then when it proceeds, I won't use the Runge-Kutta or the modified Euler method anymore.
Okay, yes, I understand. I see that this is not possible because you have more terms like n+1/2, so you need the predictor in this formulation. Yes. Okay. Another question is about the use of these block methods for solving different kind of delay problems. You have used in the case of constant delay and also the pantograph delay.
Yes.
What about the other cases? Have you solved other problems or not?
Okay, yes. Okay, so there are this type. Actually, I have a few PhD students that already solve for this different kind of constant for delay differentiate questions. So I even have one PhD student where she has solved for the retarded delay for discontinuity case. Okay, so she have done that, and also she has solved also for the time delay, for the time dependent delay, and also for state dependent delay. My PhD student, but I did not share it today with you. And then also we have go also for higher order. For Y double prime, for Y triple prime, for the delay differential equation, for retarded and also for neutral. Okay, so I have done that actually, but just for these 30 minutes, I can't share everything, but actually I have done it.
Okay, you are on the way to do a lot of work on this. Okay, thank you very much.
Okay, thank you, Prof, for the invitation.
Okay, thank you to you. Now it's time for the next speaker. Please, Gurjinder, do your preparations.
Okay. Thank you, sir. Now I will share my screen. Sir, is it visible to all?
Okay, we can see your screen now.
Okay, so thank you very much for inviting me in the conference. So today I will present on an
But please,
efficient.
sorry. Your presentation? Ah, okay. Because we are seeing Google on your screen.
Okay, just. Now is it visible?
No, we still can't see your slide.
Okay, just. Please say if
Now.
it is visible. Is it visible to all?
Yes. We can see now.
Yes, we can see.
Okay. Thank you. Today I will present on an efficient optimized hybrid block method for integrating initial value ordinary differential systems. It is known that many physical phenomena, when written in mathematical language, result in differential equations, and very few of them can be solved analytically. Thus, to find approximate numerical solution of differential equation is one of the major problems in applied mathematics. Today, this talk is just concerned with finding approximate numerical solution of first order initial value systems of ODEs. There are many suggestions when we have these type of systems. For example, when we discretize damped wave equation with the help of method of lines based on space discretization, we have a system of first order IVPs in ODs. This is just one example. There are many other situations when we have these type of systems. Now let us take our problem of the present interest. A first order initial value system of ODs can be defined and as it is done in question number 1. In this equation, Z denotes the vector of unknowns and T is the independent variable, which is usually represent time variable. So this is our today's problem of interest. The first step towards finding approximate numerical solution of system given in equation number 1 is to discretize the interval of interest, which here is the case Tn, T0 to Tn. Note that the system 1 is a continuous problem and we want to write its discrete version. For that, the interval of interest can be discretized as follow. We discretize it as Tn is equal to T0 plus Nh, where n could be 0, 1, 2, 3 up to n, and h is the space difference between the nodal points. Tn plus 1 means Tn. Here h is the step size, which may be constant or variable along the integration interval. So to the presentation, we first develop the method with the constant step size. To proceed further, let us define some notations. In the presentation, the notation ZT denotes the true solution of the system, and Zn is the approximate solution of the system at the nodal point Tn. So first we recall some well-known existing classes of methods for solving the system given in equation number 1. These are Taylor series method, Runge-Kutta methods, linear multi-step methods, hybrid methods, rational methods, and block methods. As you know, today's presentation is concerned with hybrid block methods, so we first recall the features of these two methods. Hybrid methods, first we will talk about hybrid methods. Hybrid methods were developed in order to bypass the first request barrier existing for linear multi-step methods. According to this barrier, a linear k-step method can attain maximum order k plus 1 if k is odd and k plus 2 if k is even. In the development of these methods, information of the solution at the intermediate steps, we also call these steps off-step points, is utilized. In this way, we can bypass the first Dillquist barrier. These methods are also called modified linear multi-step methods. Now we will talk about block methods. These methods were firstly proposed by Milne for getting starting values for predictor corrected methods. Initially, these methods were used as just subsidiary methods, but Roser were the one who considered them as general purpose codes. The feature of these methods is they produce approximate solution at the several points simultaneously. Now we will talk about hybrid block methods. Now in these days, a combination of the methods are developed which is based on the two approaches, that is hybrid and block. So these type of methods include features of both the hybrid and block methods. But our today's presentation is just concerned with the optimized hybrid block methods. Now we recall what are these and how to develop these methods. Earlier, hybrid block methods were developed in non-optimized version. Means these type of methods are developed by choosing just arbitrary off-step points. But Ramos et al., the one who firstly proposed the idea to develop optimized hybrid block methods by considering appropriate off-step points. They theoretically justified the choice of appropriate off-step points. Now, many authors are developing optimized hybrid block methods for integrating the system given in equation number 1. Here, I recall the step-by-step procedure to develop hybrid block methods. In the development of the method, a theory of interpolation and collocation has been used. So here I list some steps that could be followed in order to develop optimized hybrid block method. As a first step, consider an interpolating polynomial with unknown coefficients that approximate the true solution of the problem in some block of points. As today's presentation is concerned with one-step block method, so let us say the block of points is one step, that is tn to tn plus 1. This is a generic interval. As a second step, impose some appropriate interpolatory and collocation conditions on the polynomial using the points of interest, including some off-step points in the block. Off-step points means we have the interval tn to tn plus 1. We can choose some arbitrary points within this block of points. Using these conditions, we get a system of equations in unknowns of the polynomial. The system that we will have will be in the unknowns, which are the coefficients of the polynomial. As a fourth step, solving this system of equation, we get values of the unknown coefficients of the polynomial. Then we have a method with continuous coefficients. Then by evaluating the polynomial with known coefficients, as we have already obtained the coefficients of the polynomials in step number 4, then by evaluating the polynomial with known coefficients at the points of interest in the block, we get a hybrid block method. Finally, we will use the optimization strategy which is proposed by Ramos et al. In that optimization strategy, by exploring local truncation errors of the methods in the block, we can get optimized hybrid block method. Now we will show you a development of the optimized hybrid block method in which we have followed these steps. For convenience, we will just consider the scalar case. That is, in this presentation, we consider the development of the method just for the scalar initial value problem. For that, as a first step, we do the same thing. We consider an interpolating polynomial which is denoted by qt. The degree of the polynomial is 5, means we have considered a 5th degree polynomial to approximate the solution of the given system. The true solution of the system is z, and we have considered its approximation by q. And we have considered this approximation on the one-step block, that is tn to tn plus 1. And in the development, as I already mentioned, we will consider the constant step size, and further we will see how to put this constant step size into variable step size formulation. In the approximation 2, here z's are the unknown coefficients of the polynomial that are to be determined, and here theta j are the basis functions. Simply speaking, 2 is just an interpolating polynomial of degree 5 that we are going to use for finding approximate solution of the given system. Second, we consider 3 of step points Tn plus V1, Tn plus V2, Tn plus V3 with the condition that these 3 points lies in the one step block, which is Tn to Tn plus 1. Among these 3 of step points, we fixed one of step points, means we will fix the second of step point, which is Tn plus half. Basically, it is the midpoint of the block, and we will try to find the appropriate values of the other 2 of step points, which are Tn plus V1, Tn plus V3. Now see how do we do that. We impose some appropriate interpolatory and collocation conditions on the interpolating polynomial and the true solution of the system. As a first condition, we assume that the true solution and the approximate solution match at the point Tn. As a second condition, we assume that slope of the system and slope of the interpolating polynomial both are same at the points Tn, Tn plus V1, Tn plus V2, Tn plus V3 and Tn plus 1. So basically we have imposed these 2 conditions, which are called, the first condition is called interpolatory condition, the other condition is called collocation conditions. We have imposed these 2 conditions on the true solution and the interpolating polynomial. Using these 2 conditions, we will have a system of equations in unknowns of the polynomials. Note that xi j are the unknown of the interpolating polynomial. So ultimately, using 3 and 4, we have a system of 6 equations in 6 unknowns. So one can solve this system of equation by using any computer algebra system, because in computer algebra system there are many built-in functions that can be used to solve these type of systems. We have solved this system in Mathematica using the command solve, which is a built-in function in Mathematica. Solving this system of equation, we get the values of the unknown coefficients of the polynomial, which are xi0, xi1, xi2, xi3, xi4 and xi5. Now substituting back these polynomial in equation number 2, we get the method which is written in the simplified form in equation number 5. Note that here all the coefficients of the method are continuous, and we have used some notations. Z, as I already mentioned, it is the notation for the true solution. Zn, it is the approximate value of the solution at the nodal point Tn, and the capital F notation is used for the right hand side of the slope function, or you can say right hand side of the system. Now our purpose is to find the method. For that we evaluate the equation 5 at the nodal point Tn plus 1. In this way we get the main method that approximates the solution of the system at the point Tn plus 1. As we need some other additional methods that can be obtained by evaluating the polynomial which is given with known coefficients in equation number 5 at the off step points Tn plus V1, Tn plus V2 and Tn plus V3. In this way we have 4 methods in 4 unknowns. The unknowns of the block method we have Zn plus V1, Zn plus V2, Zn plus V3, Zn plus 1. Now our major objective is how to find the appropriate values of the off step points. Note that all these methods, when we write these methods in simplified form, these methods will depend on some parameters which are V1 and V3. Now our objective is how to find the appropriate values of these two of step points, which are V1, which are corresponding to V1 and V3. For that, we will expand the methods at the nodal point Tn plus 1. This is the method at the final point of the block, and method at the midpoint, which is Ztn plus half. Means we have considered two methods, one at the final point of the block and other at the midpoint of the block. Now we will use optimization strategy proposed by Ramos to find appropriate values of the off-step points. Now see how do we do that. For doing that, we expand these two methods, means method at the final point of the block and method at the midpoint of the block, in terms of Taylor series about the nodal point Tn. By expanding these two methods using Taylor series, we get the local truncation error, which are written in equation number 6 and 7. The local truncation error written in equation number 6 is the truncation error of the method which approximate the solution of the system at the final point of the block, and the local truncation error which is mentioned in equation number 7. This is the error for the method that approximate the solution of the system at the midpoint of the block. Now, in order to find appropriate values of the off steps corresponding to V1 and V3, we follow the optimization strategy, which I already mentioned. Okay, we have this strategy first time in the literature by Ramos. So to following that strategy, we let the coefficients of the principal terms of the local truncation error in 6 and 7 equal to 0. Now see, we have a system of two nonlinear equations in two unknowns. Here the unknowns are V1 and V3. We can solve this type of system and to get the values of the V1 and V3. So in this way, we can practically justify the choice of the appropriate off-step points. Again, this is a system of two nonlinear equations and two unknown. We have many built-in tools in computer algebra systems, for example in Mathematica. By exploring those built-in functions, we can solve these type of nonlinear systems. Solving this nonlinear system, we get the values of the V1 and V3. Value of the V1 is approximately 0.2 something and value of the V3 is approximately 0.78. Now see the choice of these appropriate values. What will happen if we substitute these values V1 and V3 in equation number 6 and 7? Then we have gained one order in, as we can see in 8, and one order, we have gained one order as we can see in equation number 9. It means these values are the appropriate choices for V1 and V3. Note that we have many other choices because the values V1 and V3 lie between 0 and 1. If we do not follow this strategy, then we have infinitely many choices for V1, we have infinitely many choices for V3, but we want to find appropriate values for V1 and V3 that we have followed, that we have obtained by following the optimization strategy. Now using these values, in equation number 5, the complete coefficients of the hybrid block method can be written in more compact form. In this table, we have mentioned just the coefficients of the block method. So the first row indicates the coefficients of the method that approximate the solution of the system at the point n Tn plus V1. The second row contains the coefficients of the method that approximate the solution of the system at the nodal point Tn plus V2. The third row indicates the coefficients of the method that approximate the solution of the system at the nodal point Tn plus V3. And the final row, which is for the main method, this row contains the coefficients of the method which approximate the solution of the system at the final point of the block. Simply speaking, this row is the main row because it is concerned with the coefficients of the main method. So by using these methods simultaneously, we can produce approximate solution of the system at the nodal points Tn plus V1, Tn plus V2, Tn plus V3 and Tn plus 1. Means this is the feature of the block because it produces simultaneously approximate solution of the system at several points. This method also contains the feature of the hybrid because we have utilized the information of the solution at the intermediate steps in the block. Now we will discuss about some characteristics of the method. I will not show here you the whole calculation work behind this because we have time constraint, but we have calculated the following features of the method. This method has at least fifth order of convergence. It is consistent, zero stable and astable. As you know, astable is the favorable property for solving step system. Means the methods that possess this type of property are widely used for solving step systems. Further, the discussion that we have discussed just based on the constant step size of the method can be formulated in variable step size mode. In order to formulate the method in variable step size mode, we have followed the embedded type procedure. Let's recall the embedded type procedure. In embedded type procedure, we consider two methods of different order, say of order P and order P plus 1. The lower order method is used to estimate the local error at each step of integration, and the higher order method is used to approximate the solution the lower order method is used to estimate the local error at each step of integration, and the higher order method is used to advance the integration process. In this case, we have used fourth order method, which is given in equation number 10, to estimate the local error at each step of integration. Note that the function evaluation used in this method, we have fn plus v1, fn plus v3. These function evaluations are also used by the main method. It means using this method, there is no extra function evaluation cost. In embedded type procedure, a pair is selected which share this property. So following the embedded type procedure, we have developed one more method that share the same function evaluation with the main method. So now we have two methods. One is our proposed method that is of at least fifth order, and the other method that is of fourth order. Now we can use these two methods using the embedded type procedure. Finally, we have carried out some numerical experiments using the variable step size formulation, which is based on the embedded type procedure, in order to solve some well-known initial value systems of ODEs. As a first example, we have considered Robertson's chemistry problem. It is a system of three nonlinear ODEs, and we have integrated this problem over the interval 0 to 40. We have fixed some parameters which are required for variable step size formulation of the method. One is H initial step size that we have denoted by H ini, and other parameter is tau, which is the predefined user tolerance. We have fixed these parameters in order to use the embedded type procedure. So the reference solution for this system we have considered at the final point, which is given by Z1, Z2 and Z3. So this reference solution would be used in order to calculate the absolute error at the final point. For comparison purposes, we have considered two well-known methods. First one is the Redau method, which is a variable step variable order method, and other one is OD15S. This method is also variable order and variable step. Basically, this is the OD solver. You can say it is a built-in function in MATLAB, which is specifically used for solving step system. We have specifically considered these two methods in order to check the performance with our method. The new method that we have discussed in this presentation is denoted by OPT-HBM, means optimized hybrid block method. This is just a notation that we have used in our presentation. Now let us discuss about this table. The first column represents the initial step sizes, Column second indicates the tolerances. The third column is related with the methods that we have chosen. The fourth column is the maximum error, and fifth column indicates the function evaluation used by each algorithm. The last column indicates the computer time, which is measured in seconds. Here you can see the performance of the optimized hybrid block method is better than other methods. For example, you can see in terms of accuracy, in terms of number of function evaluations, and in terms of CPU time. Similarly, if we talk about with the second parameter, we have again the better performance. As a second example, we have considered well-known gears problem. It is also a system of 3 nonlinear equations. We have integrated this problem over the interval 0 to 50 by fixing some parameters. We have fixed some parameters like initial step size and tolerances. We have used the reference solution at the end of the point, means Tn is equal to 50. So this reference solution is obtained by using the ndsolve command in Mathematica, which is based on the 10th order implicit Runge-Kutta method. Now you can see the performance of the method. Here you can see the method for the parameter when we take initial step size 10 raised to power minus 1 and tolerance 10 raised to power minus 11, the method performs better in terms of accuracy, function evaluations, and computer time. Similarly for the other parameter. As a final example, we have considered Bruce-Later system. This is a system of 2 nonlinear equations. So we have integrated this problem over the interval 0 to 20, and we have used the reference solution obtained by 10th order implicit Runge-Kutta method. Again, we have fixed some parameter in order to check the performance. Now the results are presented in this table. Here you can see the new developed method performs better in terms of accuracy, function evaluations, and computer time. Finally, I will conclude the presentation. In the whole presentation, we have discussed briefly about the features of the optimization strategy, hybrid and block methods. As a second point, we have discussed development of an optimized hybrid block method using the theory of interpolation and collocation. Finally, some numerical experiments have been presented in order to show the performance of the method. In the presentation, we have used the following references. The first reference is the concern with the optimization strategy that we have used. Second, third, fourth, fifth, and sixth methods are related with the well-known books, and sixth and seventh methods are good papers from where we have selected some systems to carry out the numerical experiments. Thank you.
Okay, thank you very much. Now, let's see, there are some questions. Now, it seems that there is nobody that wants to ask you. I want to ask you, or maybe I want to give you a comment about these methods. When you optimize the formulas to take the appropriate parameters, you take 2 formulas, and the principal tends on the local truncation errors. So yes, why not to take 2 tens in the main formula? Because in this way you should have a greater order, and in this way in the points of interest you can get say super convergence on these points. So the block method, the global method, we will have the same order possibly, but at the points with integers indexes, you have better convergence.
Yes, sir, we can do that. In that way, we will have the main method with more accuracy. So we can do that.
Okay, thank you. So now it's time for the next speaker. So please, Rayat, do what you need to present your talk.
Hello. Hello, Dr. Ramos. Am I audible?
Yes, you are audible.
So first, I would like to thank Dr. Ramos to give me the opportunity to contribute in the talk on the use of block methods for differential. So let me present my screen here. Is that my screen is visible?
Yes, now we can see your screen. Go ahead, please.
Just a minute. So hello everyone. I am Rajat Singla from Department of Mathematical Sciences, IK Gujarat, Punjab Technical University, India. So we all are here to discuss the numerical solution to initial value problems. In that regard, we will discuss the development and analysis of a two-parameter class of optimized hybrid block methods for solving first-order differential systems. So before discussion, it is necessary to introduce the research problem. As we all know that formulation of many physical structures results in system of initial value problems. In many phenomena, we are not faced with a single differential equation, but with the system of m simultaneous kth order equation. For instance, mass movement under the action of force, problem of orbital dynamics, so chemical kinetics, etc. So here we discuss the case for k is equals to 1, that is system of m simultaneous first order initial value problem. So here is the definition of first order initial value problem named as equation number 1. So in solving, in approximating the solution of system 1, we have to follow some criteria. That is, first we have to assume that the system is well posed and has a unique continuously differentiable solution. Then we will discretize the interval of interest x0 to xn initially with the constant step size at h defined here. Then we will denote the numerical solution of system as at final point of block as capital Yn, and its kth component at the final point of block is denoted as a Ykn. Next, we will discuss some literature in the brief. In literature, there are many well-known classes of methods exist that are widely used to approximate the true solution of one. These are mainly categorized into two classes, single-step methods and linear multi-step methods. Under single-step methods, there are family of Taylor series method, Runge-Kutta methods, etc. are there. And under linear multi-step methods, there are family of Adams-Bashforth method, Adams-Moulton method, etc. are there, whose structures are defined in this presentation. Apart from these classes, there are some new classes of methods that are hybrid methods and the block methods. For the detailed survey of different classes of methods, one can consult the books by Butcher and the Harrell, and also references therein. So as our today topic is hybrid and block methods, so we will discuss some characteristics about the hybrid and block methods. Hybrid methods were simultaneously proposed by Gregg and Stetter, Butcher and Gehr in 1964 to 65. In 1955, there is a comment by Kepler that extrapolation and substitution methods are the two extreme ways in solving numerical solution to differential equation. The construction of hybrid methods is the important step into the no man's land described by the Kepler. So the construction of hybrid methods makes a bridge between the extrapolation and the substitution methods. These methods were developed in order to bypass the zero stability barrier, or we can say that a famous Dahlquist barrier, which states that as we know that the k-step linear multi-step method is capable of having order 2k, but if to satisfy the zero stability property, then there is a bound on the order of linear multi-step method, that is maximum attainable order is of k plus 1 if k is odd and k plus 2 if k is even. That is the reason that sometimes these methods are also known as modified linear multi-step methods. The main characteristic of this method is that it utilizes the information of numerical solution at the intra-step points. Now we will discuss some characteristics on the block methods. The block method were proposed by Milne for getting starting values for predictor corrector methods, but later on Rosser used them as the general purpose codes. The main property of block method is that it produces a solution at several points of interval of integration simultaneously. Now we will discuss about some characteristics of optimized hybrid block method, or we can say that why we use optimized hybrid block methods. Implementation of hybrid method uses the information of solution at off-step points, which makes it more costly in terms of computational efforts. In order to limit these efforts, the block methods were incorporated with the hybrid methods to have solution at several points simultaneously, named as hybrid block methods. Initially, the hybrid methods were constructed in order to bypass the Dahlquist barrier with arbitrary offset points. Then Ramos et al. Firstly proposed a methodology to choose the appropriate values of offset points by achieving higher order of accuracy of solution at several points. Ramos also theoretically justified the appropriate choice of offset points. So in the next, we will discuss the development of the two-parameter class of optimized hybrid block method. So we developed the class of methods for solving the scalar case of 1, that is for m is equals to 1. The derivation of the method is divided into the following steps. As a first step, we choose an interpolating polynomial as an approximation to the true solution of the problem given as equation number 2 on the generic one-step block of points, that is from xn to xn plus 1, where Cj's are the unknown coefficients that to be determined and Ψj is the polynomial basis function. To make the, as a step number 2, to make the proposed method of hybrid nature, we choose some intra-step points that are xn plus r, xn plus s, xn plus u, and xn plus t belongs to xn to xn plus 1, where xn plus k is defined as xn plus k times h. In the third step, we have to find out the values of unknown coefficients. So in that, we impose the following interpolatory and collocation conditions on the solution yx and the polynomial function xix, which are denoted as equation number 3. After having these interpolatory and collocation conditions, we get a system of 7 equations in the 7 unknowns that can be solved by any computer algebra system in order to get values of unknown coefficients Cj of the interpolating polynomial 2. Inserting the values of coefficient Cj into an equation number 2, we get a very cumbersome expression which can be written in the convenient form as below, which is named as equation number 4. Now we evaluate the expression 4 at the main point and at the off step, that is xn plus 1 and xn plus s, to get the approximation of the theoretical solution yx at these points. Kindly please note that these formulas are in terms of intra-step points xn plus k for k is equals to r, s, u, t, as the expressions are very cumbersome, so we are not including here. in the next step, as it is an optimized hybrid block method, so we want to find out the appropriate values of the op-step points u and t by keeping r and s as a free parameters. So we use these formulas, that is y at xn plus 1 and xn plus s, to get the appropriate values of u and t by using the optimization methodology. So this methodology states that in the first step, we obtain the local truncation errors of the formula for y at xn plus s and xn plus 1 by expanding them in Taylor series about the point xn. So here are the expressions. Equation number 5 denotes the local truncation error of the y at xn plus s and xn plus 1 in the terms of capital A and B, C and D. As these expressions are very cumbersome, so we write it in the form of A and B and C and D, where A is denoted as minus 7r, 2s minus 10tu, minus 3s square, 1 plus t plus 2u plus 5s, t plus u plus tu. So these are the very cumbersome expressions, so we divide it into some other parameters, that is A, B, C and D, whose values are written here as it is. Now in the second step, we equate the principal terms of local truncation errors to 0. We get a system of nonlinear equations in the form of A, B, C and D. So after solving the above nonlinear system of equations, we get the optimized values of u and t in terms of free parameters r and s. So that are written here as below, the value of u and t in terms of r and s. So in the last, we evaluate the expression 4, same expression 4, at the other op-step points, that is at xn plus r, xn plus u and xn plus t, to get the approximate solution at other intra-step points. So now we insert the values of u and t in terms which are obtained in terms of r and s in the formulas to approximate the solution y at xn plus k. Hence we get here a 2-parameter class of optimized methods for solving differential systems 1 numerically. So here we have a 2-parameter class of optimized methods. Now in the next slide, we will consider the special case of 2-parameter class of optimized methods by choosing the arbitrary values of r and s. That is, r is equals to 1 by 3 and s is equals to 1 by 2. So by inserting the values of r and s in the optimized values of u and t, we get the value, the appropriate values of u and t are given by this expression. So one can see that using the optimized values of r, s, u and t into the local truncation errors 5, that is obtained in step number 1, this one, the higher order of accuracy is achieved, that is of order 7. So now finally evaluate the expression 4 at the off-step point xn plus r, xn plus s, xn plus u and xn plus t, and at the main point of the interval, that xn plus 1, with the optimized values of r, s, u and t, we get the complete hybrid block method whose coefficients are given in the following table, where the first row denotes the expression for the approximate solution at the off-step point xn plus r, and the second row denotes the approximate solution at the off-step point xn plus s, third row denotes the at xn plus u, and fourth one denotes the approximate solution at xn plus t, and the last row, which is the most important one, shows the main formula or the approximate solution at the xn plus 1. So we have divided this table into 2 tables. So this is the proposed block method, structure of the proposed hybrid block method. So next we will discuss about the analysis of the method. After having theoretical analysis, following points were concluded: that the method has at least 6 algebraic order of convergence, the method is zero stable, the method is consistent, and the proposed method is conditionally stable, whose absolute stability region is showed by the given figure. So in the next step, now we will discuss, in the next slide, now we will discuss about the formulation of proposed method into adaptive step size mode by using embedded type procedure. In this approach, a lower order method is considered to get the estimation of local truncation error at each step of integration. Here we choose the lower order method in such a way that it uses same function evaluations as the main block method. So this is the lower fifth order method that will be used to estimate the local error at each step of integration, which uses the same function evaluations that were used by the main method, that the main proposed method. So here is the pseudocode to implement the proposed method into a variable step size mode. So I will briefly discuss about this code. Approximate the solution as a step 1. Approximate the solution of problem 1 using the proposed block method whose coefficients are present in the table at grid point xn plus 1 with the available information of the solution at the point xn, and take the initial step size as h old is equals to h initial. Then apply the lower fifth order method again to find the approximate solution of the problem 1 at grid point xn plus 1 using the already available information of the solution at grid point xn. Then estimate the local error by considering the difference of the solution obtained in the first step and the solution obtained in the second step. The fourth step, if the estimation is less than the toll that is predefined, the toll is the user's predefined tolerance, then we will double the step size to save the time and proceed the integration process with the h new. To avoid getting into the loop, some bounds were imposed on the new step size as h minimum and the h maximum. In case if estimation is greater than tolerance, then we revise the current step size as h new is equals to new h old tolerance by estimation raised to power 1 by p plus 1. In this case, return to the previous step and redo the computations with this new step size h new provided with the same bounded conditions. And here the new is a safety factor such that new lies between 0 to 1. In order to have the previous the new step size less than the previous step size. So in the next slide, we have performed some numerical experiments have been carried out on well-known non-linear systems. So the following notations were used while calculations. So there are some notations which were used in listed tables. To make a fair comparison, very well-known variable step size numerical integrators are used. So list of solvers used for comparisons are: number 1 is redo. This is of variable order. This is of variable order of order 1, 5, 9, and 13 with step size control and based on implicit Runge-Kutta method. Second method used for comparison is implicit Runge-Kutta method based on Gaussian quadrature of order 10, which is named as RK-Gauss. The third method used for comparison is A-stable Simpson's type second derivative method of order 6, which is named as IM block. Please note that we have used RK-Gauss and IM block in also variable step size mode using the same proposed strategy used for the proposed method that is named as EMOHB, that is embedded optimized hybrid block method. So as a first, we consider a non-linear problem and solve the problem with proposed method in both constant and the variable step size mode over the interval from 0 to 1.99. For adaptive step size, tolerance and h initial are varying to equalize the number of steps used in the block method with the fixed step size strategy. The data presented in table clearly reveals the better performance of proposed method in variable step size mode compared to the constant step size in terms of accuracy. In this table, the first column represents the number of steps, which is fixed for both the for the proposed method in both the strategies, that is for constant and variable. The second column denotes the number of function evaluations, which will remain same in both the modes, and the third and fourth will represent the comparison of the errors. In the next slide, from figures, it clearly shows that adaptive step size code adjusts the step size in order to capture the behavior of the true solution more appropriately than its fixed step size version for same number of nodal points. So in the left side, this is the plot of solution component y1 of problem 1 using proposed method with constant step size. Clearly, it shows that every time step size remains constant at every step on every portion of solution of curve irrespective of the nature of curve. In the right side, there is a plot of solution using proposed method with variable step size, which shows that method adjusts the step size accordingly. Where the portion of curve is smooth, it takes the largest steps as defined in the pseudocode, and where the curve is steep, it takes smaller steps to acquire the behavior of true solution. We have also plot the graphs over a small interval from 1.92 to 1.99. As we see that in the left side, it took only 2 discrete solutions as per the step size, and in the right side, it took many discrete solutions to approximate the main solution of the to approximate the true solution of the curve in the small interval. So with this, we have plotted these graphs with the same number of step size, that is n is equals to 36 for the constant as well as the variable step size mode. Similarly, this figure represents the component y2 of the solution of problem P1. So from this we can conclude that the proposed method with the variable step size mode works better than the constant step size mode. As a second example, we consider the diffusion-free Bruce-Slater system, which consists of 2 nonlinear system of equations. It can be shown that critical point of the system is y1 star and y2 star. For the numerical experimentation, we here assume that m is equals to 3 and l is equals to 1, and over the integration interval from 0 to 20, as it was suggested by the Butcher and Podesky. As the exact solution of this system is still unknown to us, so we obtain the reference solution at the final point of the interval using the 12th order implicit Runge-Kutta method. So the numerical results were computed by considering the initial step size and tolerance is 10 raised to power minus xi, and tolerance for 10 raised to power minus xi plus 3, and where xi lies between 1 to 3. So the first column represents the initial step size, and the second column represents the tolerance, and the third column represents the method for the comparison, and the fourth column and the fifth column represent the absolute errors, maximum absolute errors at the final point of the interval, and where n denotes the number of steps and f evals denotes the number of function evaluations. From the table, we can clearly see that the embedded optimized hybrid block method performs better in terms of the accuracy and the number of function evaluations. As a next example, we consider an example of Jacobi elliptic functions and solved this problem with same variable step size solvers over the interval 0 to 50. In solving the problem, the initial step size and the tolerance has been fixed for every solver, and the efficiency curve that is shown on the next slide clearly reveals that proposed method gives better results in terms of accuracy and function evaluations. Here we plot the efficiency curve before the number of function evaluations with respect to the maximum absolute error. Here we clearly seen that as we increase the small the tolerance, the higher order of accuracy is achieved by the embedded optimized hybrid block method, whereas in the IM block and Radu, after some tolerance or some initial step size, the error remains constant and just increasing the number of function evaluations. And where in RK-Gauss method, it has very low order of accuracy with respect to the higher number of function evaluations. So this efficiency curves clearly depicts that the performance of proposed hybrid block method works better than the other variable step size codes. In the next figure, we have plotted the discrete solutions of the Jacobi elliptic functions. So these are the discrete solutions. So in the last, we will conclude some remarks. So we have derived a two-parameter family of optimized hybrid block method using interpolation and collocation procedures. Variable step size formulation of the proposed method using an embedded type procedure performed better than the proposed method with constant step size strategy. Conditionally stable proposed method performs better than the implicit astable methods on the chosen problems. In spite of having at least sixth order of convergence, the methods competes the higher order implicit Runge-Kutta method based on Gaussian quadrature. Also, the proposed method performs better than the Simpson's two-step method, which uses second derivative. So the proposed method also bypasses the Dahlquist barrier, as it is a one-step block method. So by the Dahlquist barrier, the maximum attainable order with zero stability condition is 2, but the R method is of order at least 6. So at the last, some well-known problems solved numerically using the proposed solver, which justifies the better performance of the method in terms of accuracy and the function evaluations. So here are a list of some references that we used in this presentation. Thank you for attending this session.
Okay, many thanks, Rayad, for your presentation. Now let's see if there are some questions.
Yes, Professor, I want to ask one question.
Yes, sir.
Okay, go ahead, please.
Yes, Dr. Rajat, you have mentioned that while approximating your true solution with the help of the interpolating polynomial that was denoted by psi x, so there were you were calculating the coefficients Cj's, right? So I think you got a linear system and you have solved that linear system to find out those coefficients. So is there any possibility that you got a multiple solution? Because when you solve the linear system of the form Ax is equal to B, then there might be some multiple solutions. So how do you choose the values of C? Because it will, the method will be entirely different if you choose the different values of C.
Yes, sir. Then I think we have a different class of methods over there if we have a different solutions of Cj. But then we can kept some free parameters of the constants, and we will develop the class of methods for this true solution.
Okay, so the method will be different for different values of C.
Yes, sir.
Okay, so is there any criteria that how we choose those values for this particular that you have presented over here? So how did you choose those values of C?
Sorry, maybe there is a confusion here because he was asking about the solution of the system, of the linear system, to get the coefficients. But in this case, the linear system, the determinant is different from 0, so there is only one solution. So you get just one solution for the coefficients.
Okay.
Yeah.
Okay. Right.
So
got it.
The next step is to choose the parameters. So this is another question. Okay.
Yeah.
Okay.
I got it.
Now Thank you. Now related with this, with how to choose the parameters. Initially, you take 4 parameters, then you solve the system of local translation errors in terms of 2 of them. So you get 2 free parameters. So you get 2 parameter method, 2 parameter formulas. So my question is it possible to optimize the 2 free parameters R and S that you take?
Yeah, actually, my supervisor and me are working on this, that how we can get the optimized values for the free parameters so that it will make the method astable. Because here we see that there are some the values chosen for S and R the method is not astable, but we can impose some condition on these variables to make the method astable, but we are still working on it.
Okay, thanks. Just comment about the stability region. You have shortened the graph. So for the next presentation, try to put all the stability region. Okay. Okay. Any more questions? Okay, thanks, Rayat, for your presentation. Now, the next speaker is Farina Ibrahim, who is going to talk about block BDF's methods for STIF problems. Please go ahead.
Okay, good afternoon to everyone. Can you see my slide?
Yes, we can see it.
Okay, thank you. Okay, my name is Zarina Ibrahim from Department of Mathematics, Faculty of Science, University Putra, Malaysia. First, I would like to thank the organizer for the invitation to contribute in the mini symposium on the topic of block method. Okay, without further delay, this will be the outline of my presentation. So I will go through an introduction to block method. Secondly, a review on the family of the block backward differentiation formulas. Then some numerical result will be presented. And finally, concluding remarks on the family of the BDF. So as an introduction, the focus of my presentation today will be focusing on solving the first order ordinary differential equation using block backward differentiation formula. So the objective is to obtain an approximate solution Yx to equation 1. Okay, since the focus of this presentation is for solving stiff ODEs, I would like to share some definition on stiff ordinary differential equation. So there are various definitions describing stiffness are given in the literature. For example, stiff equations are referred as equations where certain implicit methods, in particular the backward differentiation formula, will perform better as compared to the explicit ones. So this definition is given in 1952 by Curtis and Hirschfelder, followed by, this is another definition for stiff problem, for which explicit method don't work, given by Harrier and Warner in 1996. Okay, another definition by Robertson, where equations that represent the behavior of a system containing a number of fast and slow reaction. But in our work, we adapt the definition given by Lambert in 1973 in his book Computational Methods in Ordinary Differential Equations. If you have a linear system, in order for you to determine whether the problem is stiff or non-stiff ordinary differential equation, you have to calculate the eigenvalue. So if the real part of the eigenvalue is less than 0, which means it's negative, then we can conclude that the ordinary differential equation is a stiff problem. So when developing the families of the BBDF method, these are the few issues that will be considered when developing the method. How accurate is the approximate solution? How to control the error that incurred at each step in the scientific computation? And how efficient is the numerical algorithm in terms of its computational cost? And finally, whether the derived method will be stable. Since we developed the method for solving stiff ordinary differential equation, we have to determine whether the stability region is suitable or not for that type of problem. And also, we have to determine the convergence of the derived method. Okay, so next I'm going to give some a review on block method, and I think this is not new. So the definition that I presented here is from Chu and Hamilton on the multi-block methods. So the given K-block R-point method. So a general K-block R-point method is a matrix finite difference equation of the form given as an equation 2, where all A's and the B's are the certainly chosen R by R matrix coefficient, and M will be equal to 0, 1, 2, and so on, represent the block number. And take note, N equals to MR is the first step number of the mth block, and R is referred as the block size. Okay, these are some of the family of the block method which I have derived with my co-researcher and also with my postgraduate student. For example, in a 2-point 2-block method, so if you can see from the figure here, the computed values is actually, what we want is to compute an approximate value at the point xn plus 1 and at xn plus 2. In a 2-point 2-block method, the computed values at the previous k block. In this case, we have 2 blocks as the previous block to approximate the current block which containing R points. So in this presentation, I will be focusing on only the 2-point block method. But you can also extend the method up to 3-point block method. Okay, this is another example which is one of the classes of fully implicit block backward differentiation formula, which is referred as the 2-point 1 block.
Please, Sarina. Sarina?
Yes, can you hear me?
Yes,
now we can hear you.
You can hear me. Okay, can
Please
you see my
go back 2 slides, more or less.
Okay.
Thank you.
Okay, can you see my slide?
Yes, we can see it.
Okay, thank you. Okay. Okay. The next formulation is on a diagonally implicit block backward differentiation formula. So the difference between the diagonally implicit and the fully implicit is on the interpolating point. So from the in the fully implicit BBDF, we are considering the future point. Instead of only xn plus 1, we are also considering xn plus 2 in the approximate value for the first point at yn plus 1. That is the difference. Okay. Okay, from the diagonally implicit BBDF, okay, these are some of the literature review. Briefly, this is the literature review on the block method. So I think I am not going to go through each of these, but I just want to highlight the family of the BBDF start in 2007 from the R-point BBDF method of constant step size. And this method is extended from time to time. Okay, this is what I mean by the families of the BBDF. First, we start with the fully implicit BBDF of constant step size, and then it has been extended to improve the performance in terms of the computational time. It is extended and modified to be a diagonally implicit, namely noted by DI-BBDF. And recently, the diagonally implicit has been extended further into a singly diagonally implicit. The reason for extending diagonally implicit to singly diagonally implicit is to reduce the computational time in the implementation using Newton iteration. Because in singly diagonally implicit, you don't have to update the Jacobian at every step, since the diagonal element in the SDI-BBDF is equal. Okay, and also these families of BBDF recently has been extended to another form, which is referred as the hybrid BBDF, by including the offstep point in the derivation of the formula. Okay, I just want to highlight again on the review of the block backward differentiation formula. As I said, the BBDF family start in 2007 using a fixed step size and also been developed into a variable step size for solving ordinary differential equation. And then in 2008, Abasi is my PhD student, extended the method of Ibrahim and solve the problem, implement the problem for solving a differential algebraic equation, and also has been tested for solving boundary value problem, and also for solving fuzzy differential equation. So all this type of problem, if you want to have the detail, it is you can search. You can search in the Scopus database, and you can find the detail of the derivation for all this problem for solving DAE, boundary value, and fuzzy differential equation. Also, starting with fixed step size, the BBDF has been extended to improve the performance by implementation using variable step. Okay, so if you can see from this figure here, it has been extended since 2007 until 2019. The latest is 2019, the hybrid BBDF. It has been extended for solving first order, and then for a second order ODE, where you don't have to reduce the second order ordinary differential equation, you can solve it directly. But for this presentation, I'm not going to cover the variable step or whether the second order ordinary. The focus will be totally on a constant step size block backward differentiation formula. I hope this slide doesn't look so complicated. What I'm going to show is actually all the families of the BDF, which has been modified from time to time to improve the performance. Okay. Let's, I mentioned earlier, the method has been extended into a singly diagonally implicit by taking consideration the definition given in the literature on singly diagonally implicit method. So I listed here a few definitions on singly diagonally implicit method, which is stated as the element in the diagonal, the diagonal element in the matrix is equal. So if you have the diagonal element equal, then in the implementation, when you have a linear system to be solved, you can save the computational time. You don't have to update the Jacobian here. You don't have to update the Jacobian at every step, since the value of AII here is the same. Okay. Okay, this also again, the singly diagonally implicit normally has been implemented for Ranjakuta method. Okay, for this one you see the diagonally implicit Ranjakuta method, and then been improved into singly diagonally implicit Ranjakuta by Ismail in 1999. Okay. Okay. For the family of the block backward differentiation formula, this will be the general form of the BBDF, the families of the BBDF, if you have 2-point block method. Okay, this is the formula that I want to share. Some of the formula derived from the BBDF and then extended into a singly diagonally implicit BBDF, and then BBDF with the off step. Number 3 here, BBDF with off step. Number 4 is the diagonally implicit BBDF, and number 2 is the latest done by my PhD student, where she introduced a parameter rho into the derivation. Okay, so and it's already being published. You can download the paper and see the detail of the derivation of the rho DI BBDF. So the method that we have derived is in the form of the predictor corrector method. So the predictor will be in the form of in the explicit form. Okay. For the second issue, once you have derived the method, you have to make sure that the derived method is stable and should possess the property of astability, since we are solving a stiff ordinary differential equation. So take note here, there is a typo here. It should be y prime, not y prime 4. Y prime equals to lambda y. This will be the test equation to check for the stability. Okay, once we have the stability polynomial, we find the roots of the polynomial and make sure that the root is within this interval, -1 and 1. If the root between -1 and 1, we say that the method is stable. Okay, for the when you plot the stability polynomial, if the region covers, if the region of the absolute stability contains the whole of the left half plane, then you can conclude the method derived is suitable for solving stiff ODE. Okay, I show you also the stability for each of the method which I've shown earlier for the singly diagonally implicit BBDF method. So if you refer to the stability region, it consists of the whole of the left half plane. You can see here, stable region. Okay. For the rho diagonally implicit BBDF also is astable. For the BBDF with offset point, also astable, and for the diagonally implicit also is astable. So from this stability region, we can be very sure, we can conclude that all the derived method for the family of the BBDF is suitable for solving stiff ordinary differential equation. So I also listed the improvement that has been done from the singly diagonally implicit up to diagonally implicit with offset point. For example, when you add the offset point is you can improve the accuracy of the approximate solution. Okay. Okay. Okay, for the convergence of the method, I will consider the definition given by the theorem given by Lambert that for a method to converge, you have to check the necessary and sufficient condition for convergence. So in this case, we have to check for the consistency and the zero stability of the method. Therefore, if these two conditions is satisfied, then you conclude the method converge. And take note also, for zero stability, the root of the characteristic polynomial or the stability polynomial should not be greater than 1. Okay. I will go into detail. Okay. The extension of 2-point BBDF. Just want to show you, in this case, you are considering 1, 2, 3, 4, 5, 6 interpolating points. Okay, this has been extended from 2-point BBDF of order 3. Okay. This one, I think I'm not going to go through how to choose the value of rho. You can read the detail of choosing the value of rho into the future value. So the detail is given in one of the paper. So you can download the paper by Haziza. Choosing the value of rho to cater for the future point here, Fn plus k minus 1. And this is the formula which already been derived. Okay, for all the BBDF method, whether it is diagonally implicit, whether it is singly diagonally implicit, whether the BBDF is of fully implicit, the method is implemented using Newton iteration. So the first step is to write the formulas in the general form, and form it into a matrix. Okay. Then use Newton iteration. Okay. So take note, for the singly diagonally implicit, the diagonal element here will be equal. That's why when you implement the singly diagonally implicit, you will have a lesser computational time. You don't have to update the Jacobian every time you change the step. Okay. Next, for the variable step size, this one I just go through briefly on how to derive the method to cater for variable step size. So take note, R here is the step ratio. So for the variable step size, either you have the first step is the same. You have to divide your interval AB into a series of blocks containing R point. So if you want to have a 3-point block method, then you divide your interval into 3 points. If you want to have a 2-point block, then you divide the interval into a series of blocks with each block containing 2 points. Then you interpolate the interpolating point using Lagrange polynomial. So I just want to highlight for the BBDF family, there is not only one way to get the coefficient. I have tried in 2007, I derived the coefficient using a generating function. So you can download that paper. The derivation is using the generating function. And then when I presented in London in 2011, I changed the derivation. Instead of using a generating function, I find it comfortable to use an Lagrange interpolating polynomial. Okay, you just interpolate the points using Lagrange polynomial. You differentiate the Lagrange polynomial, then you will end up with the formula of the BBDF. Recently, my postgraduate student derived the method using Taylor series method. So there are three ways of getting the formula. Either you use the generating function, you can use the Lagrange polynomial, or you can also use the Taylor series. The difference is if you use your Lagrange polynomial, once you get the formula, then only you determine the order of the method. If you use the Taylor series method, you decide the method of what order that you want to derive. That's the difference between the Lagrange and the Taylor series. Okay. So this is the formula that for variable step size. R equals to 1 refer to the constant step size. This one is a fully implicit. And then the step ratio R equals to 2 will be when there is a step failure in the computation, then the step will be reduced to half step. And also step ratio R equals to 5/8. This one is you increase the step size when you have a success step in the implementation. I have checked for the BBDF, if I double the step size, then the method will be unstable. Therefore, I stick to 5/8. So for the stability of the method, so I've plotted the stability for the step ratio, the constant step size, the half step, and also when you increase the step size. For the step ratio R equals to 5.8, we conclude that this one, the method is almost astable. Or you can also say that this method is stiffly stable. Only the step ratio for R equals to 1 and R equals to 2, the method is astable. Okay, this one is the general implementation where theta 1, alpha 1 referring to the coefficient of the variable yn plus 2, yn plus 1, and zeta 1, zeta 2 are the back values. So I present a few numerical results. Where the error is calculated using this term here. Okay, for problem 4, so this is the numerical result. I compared this problem with a N BBDF with the classical BDF. This implementation is using the variable step size, and you can see the in terms of the accuracy of the method, and also in terms of the computational time. Okay, for a system of two equations, I compare with the VSVO BDF. This is a classical backward differentiation formula using variable step, variable order. As compared to the BBDF, only variable step. Okay, and yet it managed to have a very good accuracy and also in terms of the computational time. Since the method is developed in block, okay, you can also see the number of integration step is nearly half. We managed to cut the integration step by half. This is another tested problem where we try to solve using various eigenvalue, mildly stiff, okay. So I think I'm going to skip this one. Okay, this one I want to show the method that we have derived by one of my student. Okay, using the off-step point. And finally, we can conclude that the family of the BBDF can improve the accuracy of the approximate solution. It is stable if you check the stability region of all the method of from the family of PPDF, it is stable, and most of the method is stable, except when you increase the step size. When you try to increase the step size by a factor of 1.6h, then it is almost stable. But still, when you get the numerical result, still you can obtain the accuracy within the user tolerance. Okay, thank you very much. I think that's all for my presentation. And this, thank you.
Okay. Thank you very much, Sarina, for your presentation. Now it's time for questions. Anyone want to ask something?
I guess no question. Anyway, for the detail of all the derivation, it's already been published. And if you need the detail, you can download the paper, because I'm not able to discuss in detail. The derivation is quite lengthy. So given the limitation the time limitation, that's all I can provide.
Okay, thank you. Concerning the results, the numerical results, the time you put in the slides was in milliseconds?
In seconds.
Seconds?
Yes.
Okay. I want to ask you about maybe is slide 20 in your presentation, because I couldn't see the number, where you compare different methods, the stability regions and the order.
Slide 20. That's one? This one?
This one, yes. So I see that there is a big difference between orders. So yes, for the block backward with all the points, you get order 6 and the other order 2 only. So why is this high difference?
Actually, what I show here is when I have the method with off step, the method is of order 6. When we check the method for off step, it is of order 6. So what we want to show is actually the method, even though it is of order 6, as compared to the order 2 method, order 6 give a better stability region. If you look at the interval here, the closed region is from 0 to 10. That's where the unstable region is. As compared to the diagonally implicit off-step point, the unstable region covers from 0 to 14. So actually this is just want to show which one is better in terms of which one having a larger stability. So actually, as I said, that's why for the off-step point, we stick to BBDF-O instead of diagonally implicit, because the stability region here, unstable region, is quite large as compared to this one. That's the reason, yes.
Okay. Thank you very much.
Welcome.
Any questions?
Okay, if there's no question, then I stop sharing.
Okay, thanks again. Okay, thanks to all speakers and to all participants in the talks. Now, this was the last talk, so this session has finished. And the next one continues at 40:45 local time in India, of course. So we'll see again this just in a few hours. So thank you very much to all. Now see you later.
Okay, thank you.
Okay, bye.
అదే టైంలో కూర్చుండే అదే కూర్చున్నాం ఆయన కూడా ఫోన్ చేసిన రాయటం కూడా మరి ఇందులో ఫోన్ చేసిన ఇప్పుడు ఇందులో బుల్లెట్ అంటుండే మాట్లాడినాను నేను